All right, so the last time we analyzed the radiative transfer equation, looking at some simple solutions of it, specifically the homogeneous slab and what that contained, and how we also could connect that to various, on the basic level, various astrophysical contexts and examples, okay? Now, today, we're going to dig deeper into some fundamentals of the radiative transfer equations. So today is going to be quite technical, I guess, to some extent. But I do wish to introduce you to some more of the subtleties, we can call it, of the radiative transfer equation. So at least you have seen it once, and you know how to do those parts, so that, I don't know, if you in the future something come across and it's just thrown up there in some course, you know that, okay, but this is the transport equation in this form, in that form, etc. And that you also, I don't know, if you want to do something like analyze the light curve of a transit light curve from an exoplanet, and you need to account for limb darkening then in order to get the parameters out of it. You know, where does this limb darkening actually come from, really? And also, I just find, I've already talked about, you know, we see roughly until optical depth unity. We define the photosphere at some sort of optical depth average 2/3. I mean, where do these things come from? And hopefully, that will be clear after today's class, where we will dig into this. So, we start again with the transport equation now along a given ray. Again, we had the ray, it was in some n hat, we had some path length delta s here. Okay, now I'm going to do a little bit of a Taylor expansion here of the intensity, moving from that to this. And actually also then take into account that it takes some time. Speed of light is fast, but it's not infinite fast, right? So you have to take the time shift also technically into account there. And then, of course, if we keep the first order terms, this is just the I nu ds delta s plus the I nu dt delta t. But then we can just see this, we can rearrange, we take down the delta s from that, we move over this, and we see that we had essentially how we defined the transport equation before, so that we can write it, in this case, in this form, which is then the I nu ds plus 1 over c the I nu dt, where of course used here that delta t over delta s is just 1 over c, speed of light c. And then we add the sources and the sinks on the right-hand side again. And then we can see that now we have obtained a different form. It's actually a partial differential equation now, when we keep the time derivative into it. Yeah? So before we start to move on with what is this ds really, I wanted to make one remark here, and that is, you see we have the nu here. So essentially, what I've done here is that I've assumed that the frequency nu does not change, right? Now, the thing is that at least when we have moving media, then that's no longer strictly true, because then we're subject to the Doppler shift. Yeah? We will come back to this Doppler shift later during the course when we discuss line profiles and line broadening in more detail. But it's essentially that when you have a source, it's the same as the traditional ambulance type of effect, right? That when you have in this case, I am, say, an atom within the moving astrophysical gas, and then I have some light coming at me from this direction. And then, of course, if I'm moving in this direction, the photons that reach me, I will see them because of the velocity in the line of sight as redshifted. If I move towards them, I will see them as blue shifted. Yeah? And that's the Doppler shift. So technically, when we have that, we have to also then take that into account, and essentially we have two options for it. So we can add it to the material interaction terms, the emission and extinction coefficients, okay? So we say that, okay, we account for the Doppler shifts when we actually calculate these terms. That's not the subject for this chapter, but for later. So that's one way of doing it. The other way of doing it is to say, okay, we're going to transform ourselves into a frame that is actually co-moving with the fluid or with the gas. We call that the co-moving frame. It's equivalent to the Lagrangian frame. Yeah. So if you do that and you transform it to the co-moving frame, then you, then you unfortunately also then have to account for the frequency derivative here in your side. So you have to add that term to this. But this is for the co-moving frame. And for the purposes of this course, I just wanted to give you that in case you encounter that. For example, if you ever move on and do research with me or my group, then you will certainly encounter this. But here we're going to just assume that we do not have any velocity for the purpose of understanding the basic radiative transfer equation. It makes life easier for us. So then we don't have to account for any possible frequency shifts. Now, okay, and we also see, of course, from this exploration that the equation of transfer is a linear equation. We have only accounted for the linear terms here. So the question now becomes, what is this DDS here then? Okay, so first we can look at, okay, we're going to put some coordinates to this. So we're going to look at it from a Cartesian coordinate system. And what is then ddx? Well, it's do I do this in the easiest well? Dx, ds, dds, no, ddx plus dy, ds, dy plus dc, ds, ddc, okay? However, here you can of course see that this is just nx, this is just ny, this is just nc, where n is our unit vector that we have introduced before. And here you see your gradient Doppler vector, so you can actually write this as n hat, scalar product, dot product with the gradient operator. Yeah? So, then we can reformulate this in the sort of neat way, the I nu dt plus n hat gradient of I nu, the mu I nu nu. So there we have that form of the radiative transfer equation. Okay, now let's assume now again that we have a 1D medium where we have variations only along, in a Cartesian sense, the vertical, so along the z direction, and we can assume that it's stationary, steady state, so d dt is 0, okay? Then we already have calculated, we know that the nc component is cosine of theta, which we typically call by mu, right? So we can just write that down. It's mu di nu di theta equals either nu or nu I nu, okay? And this is now the radiative transfer equation for a 1D stationary Cartesian situation with variations then along the z-axis. Oh, sorry. I'm going to take this first. All right. So, where we at? Mu di nu di c, either nu alpha nu I nu. Okay, we're going to keep that in a little box here. And let's discuss it a little bit. So the first thing is that this is no longer now along a ray, right? This is defined along the vertical z. Okay, along some sort of vertical axis, c here. Okay, where, you know, along the line, of course, we would have that. This is true. Okay. Now, if you look at the rays here now, this is some sort of n hat then, yeah? And this is our theta angle, okay? And then it's traveling through the media there in the direction specified by n hat, mu here. Now, what you can see and what is so nice with this is, of course, that once you have traversed a certain way within your media, and you come up here, you can just look a vertical there, then along this ray, and you put a theta 1 there, you put the theta 2 there, you see that theta 1 equals to theta 2. There is no variation of the theta angle here. There is no variation of mu, which makes life easy. Now, of course, there is a certain problem here, and that is that a lot of astrophysical objects we're interested, I mean, they're not Cartesian like that, they're more spheres, with the most obvious example perhaps being a star, as I heard from the audience, whispering very slow. Anyways, a star is a sphere. You know, it's not a Cartesian object here. The Earth is also a sphere, by the way. Yeah. If we want to think about the atmosphere of the Earth. Now, what happens when we have a sphere here? Okay, let's try to draw this. This is going to be horrible, and I apologize in advance, but we're going to try. Oh, you see? There would be something like the center of the sphere, right? Okay. And we have some second layer here somewhere. Okay. So now we have a sphere, an extended sphere. And if we now take a ray through this sphere, let's say we're sitting somewhere there, so we want a ray along our direction. Okay. Then, of course, yeah, we're going to do a radius here. It will be our R1. Okay. Then we have our theta 1 here. Okay. But then if we're going to look at, say, let's say that this is the surface of that object. And we're going to try to do the same thing here, right? Because now the variation is along these radial shells. Then theta 2, then hopefully my drawing was not so bad that you cannot tell that theta 2 is actually smaller than theta 1. So when we have a ray for this configuration, the theta angle changes. The mu angle changes. Okay? And that is not very pleasant at all, because it means that when we now evaluate DDS, we're going to have to go from just considering n hat times the gradient to also consider the change in the unit vectors. Okay? Now in full 3D, where you have two, you have theta and phi, this becomes a complete mess, because of course if you think about the spherical coordinate system, the standard notation for the polar and azimuthal angles are also theta and phi. Yeah? So in the course book, for example, then I denote them by big theta and big phi, and the radiation angles as small theta and small phi. I cannot draw that. I'm not even going to attempt. It's just going to be a complete mess. And actually, the full derivation here in the 3D coordinate system is, well, it's vector calculus, it's vector analysis, doable, straightforward, but quite intricate. If you want to see it, for example, the authoritative textbook on this subject of stellar atmospheres by Hubine and Mielas give this the full expressions. What we're going to do here today, though, is that, okay, let's assume again that we have our 1D media, time independent, we have variation along only the r-axis. We call that the spherically symmetric media. And then we can work this out, hopefully. Then can see that the DDS is going to be the RDS DDR plus the theta ds d theta in this case. Now the RDS we can just read off actually from the geometry of the situation. That is just going to be again cosine of theta equals to mu. So there we have that. The question is, what do we do with this? Well, we can realize that the constant along this ray here is what we typically call the impact parameter, and that's sine theta times r. You can try to convince yourself that this is the preserved quantity here. Now, say that this is a constant now, and then we can take the PDS on that one, okay? So that's just then dr ds sine theta plus r cos theta d theta ds, and that will be 0. But this one we already know is cos theta, so you can just cancel these out, and you get the theta ds equals to minus sine theta divided by r. So there is your variation now that you need to apply in your spherically symmetric transfer equation. So, So that was the 1D Cartesian case. And then we had said that the SDR equals minus sine theta divided by r, I think. Yeah, so we're going to do the 1D spherical case then, which will then be mu, the I nu, the r, plus 1 minus mu squared divided by r, the I nu, the mu equals eta nu, alpha nu, I nu, where I've again, of course, used here. This was, if you recall, the equation was actually the I nu, the theta, right? But of course, I've just used that mu equals cos theta and the theta, the mu, the theta, the mu, the theta equals minus sine theta to just change the variable into mu, which is typically what is done. So you can see that in even in 1D Cartesian, no, in 1D spherically symmetric media, this is a partial differential equation. We have a variation in mu that we need to take into account, and it's actually quite a bit tricky. It is what you need to apply in systems like the solar corona. If you have a stellar wind outflow from a star, or even if you have like an atmosphere around a very large supergiant star, then this is typically the equation that you need to apply. However, for many situations, there is an approximation we can use here, which is very useful. So now we're again gonna do the spherical configuration here. You see this? But now we're gonna say that, okay, the atmosphere is very thin as compared to the underlying radius, like this. Okay? And now if we draw our n hat vector here, and then we're only interested in this little layer, okay? And now we're going to see if we can do this. Probably not again. Probably you can draw it better. Then you see that this angle here, nu1, you have to draw this yourself to get an appreciation, and nu2, because this is such a thin, nu1 equals to nu2, okay? Then we can neglect the variation in theta or in mu, because the atmosphere here or the media here is so thin as compared to the complete radius of the object. And then again, okay, we neglect this variation then. We set this to 0, d mu, then we see, what do we get then? Well, we get mu, the I, the R, equals eta nu. Okay. Now, what do we see by this equation? Well, let's compare it to the Cartesian case that we had above. Are there any differences here? Yes. Exactly. So from the audience, we had that instead of differentiating in the C direction, you just differentiate in the R direction. Completely correct. And that's the only difference. So if we just replace the initial C axis by the R axis, or vice versa, we can interpret the C axis there as the R axis in our spherical system whenever we can neglect this mu angle. Now, you can even, from here, you see that the condition that has to be fulfilled for this is that delta R has to be much, much smaller than R, where R is the characteristic radius here, until the start, say, of your atmosphere, we can call this. And then this is delta R then. If this is not the case, we go back to the first case, we have the variation. However, now you can think about a few examples. The atmosphere of the Earth is not so high as compared to the radius down to the center of the Earth. The photosphere of a star, or the atmosphere of a star, is actually typically much, much thinner than the underlying radius of the star. Now, in these type of situations, this is controlled typically what we call the scale height. And that's then governed by that we think that we typically assume that an atmosphere is in what we call hydrostatic equilibrium. We have sort of alluded to that a little bit in our basic discussions here. It essentially means that the downward force of gravity is balanced by an upward pressure gradient, which for the very massive stars that I work with can actually be dominated by the radiation pressure gradient. Here on the Earth, it's the gas pressure gradient. It prevents the air from falling from the ceiling here to the floor, which, you know, wouldn't be so pleasant for us, I guess. But we build up a pressure gradient, the atmosphere. Now, the typical height of that is the calculation done in other courses here, yeah? But you can have, okay, you can do a calculation. There is an exercise for you in the booklet of this where you can just estimate it, that this is related to the so-called scale height. The scale height is typically the height over which, say, the pressure, the density in your atmosphere changes by a factor of E. And that sets a characteristic scale there. And then you can compare this to the characteristic scale of your complete object, be it the Earth, be it the star, or be it some other object, and see whenever this is fulfilled and whenever it is not. Now, this is called the plane parallel approximation. And it's indeed so we're going to now use this, and I'm going to set it up. And then after a break, we're going to do some classical solutions to this. Now, okay, so we had this, and we're going to call it the z-axis now. But we could as well, if we allude to the plane parallel approximation, call it the r-axis, right? And then, okay, we have our plane parallel layers, right? We have the z-axis, yeah? Then it's custom, so to say, to actually define now an optical depth scale, but in the other direction. So going from here inward in the object, okay? So that would be your tau nu c scale, where typically you see that at the surface of this object you would have optical depth equals to 0 in the absence of external radiation, yeah? And it increases inwards. So in that sense, you would define the tau nu c as minus alpha nu dc in the other direction, or that tau nu c from some c1 to some c2 is just alpha nu dc here. So if you plug this in now, you of course, you will see that this, you see, oh, mu, the tau nu c is going to be I nu minus S nu, where S nu is our source function again. Now, again, it is important that this now is the optical depth, not along the ray. Yeah? It is the optical depth along the vertical here and directed in the other way than the c-axis. And of course, we see that the right-hand side here have flipped signs because of this. Yes, please. Sorry? Next to the left arrow, here. Ah, yeah, this is just me doing this. No, sorry. This is tau nu c. All right, so it is the optical depth axis going here, and this should actually be a vertical line. It is not really vertical. I put a little tilt on it. I shouldn't have done that. Yeah, just down there. All right, so now we have what is actually classically the radiative transfer equation analyzed in a 1D plane parallel medium. Okay? We can see that actually we can solve this in a way that is very similar to what we did for the homogeneous slab. It's a linear OD, and we can apply an integrating factor and then solve it. So we're going to look on that for specific media after a short break now, and get to some hopefully interesting solutions which will clarify concepts like limb darkening, optical depth, etc. a little bit further. All right, let's take a break.